Hi, my name is Łukasz Langa.
And my name is Pablo Galindo.
And this is the core.py podcast, an established podcast, where we discuss internals of CPYTHON and our adventures in making a new version of your favorite programming language. This is episode 21, or as Pablo would say, episodio 21.
Episodio 21. Oh, yes. I would say that
right.
exactly. Yes.
So the podcast is reaching maturity. It could already marry and serve in the army for a while, but now it can legally drink as well. That's very timely, since it recently...
In Spain, is 18 years old, by the way. Yeah, you can drink from 18, not 21.
Same in Europe, but we're talking mostly to Americans, I guess. So, kind of...
All right.
Now it can legally drink as well in the US.
Well, I think you need to apply 150%, percentage to the drinking age. Isn't working like that? Oh, okay, sorry. Too soon.
Yes, and that's very timely, since it recently came to our attention that Apple is flagging some of our episodes as explicit.
Explicit.
Fucking right they are.
So apparently, it's very funny. The websites that support has to do this by hand. My guess is that they are using the transcripts. They are looking for fucking, which I say a bunch of times.
Yeah.
And then they mark it. It's either that or someone in support is really a fan of Core.py.
We don't know. But what we know is that the Zen of Python teaches us that explicit is better than implicit. So we'll take it. We'll take
fucking explicit, just that it's...
Yes. So with this newfound maturity, we are ready to finally cover the topic of garbage collection.
Like grown men or people.
Yes. Before we get there, though, some sports news.
We
should have a jingle just for that too, I guess. Maybe for next season.
Chop.
So Karl Mayer's hockey team, the Bellingham High Sticks, sadly lost their playoff game for third place.
What do you mean? No.
Well, given that only statistics of in-season prevented them from playing for first place, I believe that the league is exceptionally evenly matched. So that gives me hope that next season the High Sticks have a shot at winning the league.
Well, this keeps it interesting, but I don't know.
It does.
Damn. Now,
what would keep it even more interesting if those games were somehow streamed or available so that we could actually watch what is happening in Bellingham. Currently, we only sort of know the scores the day after, old men with newspapers in the days of yore. But in any case,
wait. So if they lost again, will they be collected like garbage? Okay, that's it. Okay. Yeah. Whoopsie. Sorry, Carl. I'm not implying anything.
All right. So let's talk about the garbage collector.
The garbage collector. Explicit. All right. So this should pick up from our episode from memory management. So you have not listened to it, you should listen to it. I think it's also explicit. Not all the episodes are explicit, but this one in particular it was. And then we will also recommend the episode on reference counting. Very recent episode. Very good. So okay, but now the big problem, Gukish. What is the big problem with reference counting?
Well, the big problem with reference counting is that if I refer to you and you refer to me, then we're both holding hands, and now...
That's illegal!
Yeah, we will never reach reference 0 because I refer to you and you refer to me. So there's a cycle.
Maybe that's the way Carl can avoid the high stakes to be collected. They just need to... They just need to refer to some other team. Exactly, it's cycles. So reference can't work until we have this cycle, and we never have cycles in Python. Never, right?
That never happens. Only very rarely. That is 60% of the time.
Exactly. Yeah. Very rarely. One example of this, Gukesh. One creative example of this, of a cycle. What will be the classic example of a cycle?
A classic example of a cycle which we do clear, so it's not actually a cycle, in practice, but we needed to make something special for it not to be a cycle, is when you have an exception that holds on to the traceback. So,
oh, wow, that's a very advanced example of a cycle.
so if you want to have like a very simple example of a cycle, like user created would be if you want to have some list that loops, right? Or if you have a double linked list, or if you have a tree that goes both ways, so you can traverse it both ways.
Exactly.
But those are user-defined sort of kind of structures, so that things that people write, like the exceptions, is something that Python just does the cycle for you.
All right.
So we actually had to fix this, right? But like by default, it would.
Right. The list is actually a very interesting one. Like the easiest way, as Gukesh is mentioning, is having a list and append the list to itself. You can do that. It's the magic of references. And this highlights two things. One of them is like, wow, the list contains itself. It's kind of a graph now. The other thing is that, like, how do you print this now without crashing? You know what I mean? Because like now, let's say you are implementing the REPL of the list. You will say, oh, I just iterate over every element and then I call REPL on that. Mistake. You fail. You fail. You fail because the list can contain itself and you will loop forever. No bueno. No bueno. So this highlights how hard it is to be a core developer. Not only is it really annoying because you need to deal with like a lot of shit. That's our explicit marker now. Sorry, Apple. But also, you need to add a stupid amount of complexity even for the stupidest operations, like printing the wrapper, the list, right? So that's bad. But if you skip that part, then the problem is like, how do we get rid of this list now? Because reference counting is not enough, because the list can contain itself as many times as is possible. And the hint is now this thing is a graph. We're going to need some graph algorithms here.
Yep.
And that's the solution. The GC that Python has is a very specific kind of GC. There is many ways, each one more pedantic than the previous one, to refer to this particular kind of garbage collector. But it's technically called a cycle collector to distinguish from the big boy collector. The big boy collector is the full like object collector, which does like something like the PyPy interpreter does, for instance, or like Java has. Well, Java has like 6 million of them, but like, most of them are mark and sweep. That's the big boy collector, and it just collects absolutely everything. But this, dear listeners, is the first thing that you must understand about the GC in Python. It doesn't take care of everything. It just takes care of the garbage of reference counting, which is cycles. Reference counting has its own house clean, and then when it cannot deal with these cycles, it puts them in the garbage, and then just it deals with that garbage. That's the garbage of the garbage collector of CPython. Only cycles. Okay. So how does it clean the cycles, Gukesh? Do you know? Do you happen to know? If you only have a friend who did like an entire talk about this topic in PyCon US. Damn. Or if you only have a friend who wrote an entire document, very popular, about this topic on the dev guide, which was moved recently to the CPython repo.
Yes, and that's better because like now it lives in the repository, so it is correct to the current commit that you're looking at, which obviously things change. We're actually going to be talking about the changes today, so it's good to have the documentation close now.
Right. Yeah. Shout out to Edith who did that work.
Right. Yes. So reference cycles, for them to actually be fixed, first you need to be able to traverse everything, right? So now you have to like somehow know what's in the garbage. And for Python, we have the memory representation of a Python object in memory in C has a structure, right? Like, and that structure like has everything that you know about how this object behaves, what you can do with it when you create it, whether it's slotted or not. Like there's a bunch of things in it. And one thing that is designed with garbage collection in mind is that there is a head structure for garbage collection that has 2 pointers that are literally previous and next.
Exactly. Which is very sneaky, by the way, because normally the PyObject structure, the base structure of every object in Python, basically like the pointer, right? Like that's what Python handles around PyObject.
Yeah.
That has the basic thing like type, like a pointer to the type and the reference count and whatnot. But the head that we are talking about here, which only, by the way, only objects that support the garbage collector have, not every object has this. for instance, strings that don't have it because like they don't participate in GC. Okay, so this head is before the pointer. This is the first sneaky move that CPython does, which, like, by the way, if you are not used to C, it's a bit mind-blowing because you kind of allocate a chunk of memory, you malloc a chunk of memory, you put the header, and then you put the Python header, like the Python object, like reference count and whatnot, and then the pointer points to the middle. So it doesn't point to the beginning of the allocated region, it points to the middle because that's when the Python header starts, right?
Yeah.
And then you can lie to everyone and tell like, oh yeah, this is my memory address.
But this is good,
yes,
because that thing is considered sort of like an implementation detail for Python, and it's private. So the pointer that you're getting, you can reference things going forward, but you cannot ever be sure what's going to happen if you're actually going to like go left in the memory region.
Exactly.
The reason why that is important is that, well, maybe you have free threading. Maybe you have a different garbage collector that has different things in memory. So you don't want to expose this. Maybe you're going to have an entirely different algorithm in a future version of Python. And what? Like, if that would be part of the pointer, it would break all the C API using programs, which would be terrible.
Correct. And you are raising very important points here. One of the important points actually is that this header, the GC header, which only contains 2 fields, is extremely overloaded with bullshit. In particular, you will need more than 2 fields because you will say, wow, the entire state of the GC only fits in 2 pointers? No, but like, yes, like in the sense that those if you go to the header, the pointers are called previous and next because they form a double linked list.
Yes.
Or several double linked lists. We will talk about it in a second. But you will say, well, how do you know if the object has been collected or not? Well, that's a bit. Where is the bit? Well, it's in the pointer. How is that possible? Lucas, how is that possible? It's impossible. How do you store more than a pointer in the pointer?
We actually do this increasingly now in Python using this sort of weird thing where when we were little, we had 8-bit computers. They were tiny. The memory that they could address was also tiny. And then we had 16-bit computers and 32-bit computers. And then came 64-bit computers.
64.
And now, do we have 128-bit computers? Do we want that? Like, is that going to be necessary?
No.
Right? Like, but why not? We had like 8, 16, 32, 64, so there's no more progression to 128. Why not?
Because 128 is like too big. Like, that's not bueno. Like, do you want 128 integers? Like 0 now is 128 bytes.
But why doesn't mean it's too big? Like, you have like, you have so much memory now, like that's fine, I guess. And you have CPUs that would just handle those pointers and everything. Like, you would have registers that are wide enough. So like, why doesn't it make sense to invest in that?
I mean, because you don't need it, no? Like 64 bits is already insane.
That's the thing. The maximum values in 64-bit integers are so humongous that they are literally kind of crazy to, think as insufficient, right? I know it's famous last words with the 640 kilobytes, of RAM and whatnot, but for memory addressing in particular, to use all of 64 bits is impossible currently. It is just impossible.
Well, not only that, like I think one of the discussions that happened during the discussion of object immortalization was that if you have a 64-bit integer, and if you have a normal CPU these days, like even a gaming computer, just adding 1 to the integer to reach the maximum value of those 64 bits, you will need like insane amount of years. Like that CPU will keep spinning forever. Yes, that's how many values there are.
That means this is this much memory that you cannot even you cannot even sensibly increment it by 1 to like overflow it in time. So how about we don't do 64-bit integers, but say 32-bit integers, or 48-bit, or 56, or 60. Let's just what you can actually do.
Sounds disgusting.
Yeah, but what you can do is to decide that some of the bits that are in that integer are not going to be part of the address. Instead, they're going to be tags because they're bits, right? You can either set them to 1 or 0. And those pointers are called tagged pointers. And that allows you to store additional information.
Wait. Yes, but Yes, but there is one key thing that we have not said why this is possible. Because if you just say this, it will be as confused as I was when people told me this for the first time. The key here is that memory addresses, and this is only true for memory addresses, they are aligned at 16 bytes. Right? The key here is that memory addresses, like pointers returned by malloc, and this is only true for like the system VABI and a bunch of shit, but like I'm probably more. But like all of the pointers that malloc will return and memmap for that. Well, I mean depending, but like mostly yes. We'll have the three like less significant bits unused. Like it will be 000. So all the pointers ends in 000 if you look at the binary representation. But that's a property of pointers. And only because like allocators do this because like they reasons. But like it's not because 64 bits or like it can be untrue. Like indeed, like we used to have a bag in PyMalloc that was returning things aligned to 8, not 16.
Yes.
Yes.
But that's alignment.
Yeah, but the alignment is what gives you the 3 least bytes free. If they were not aligned, what prevents a pointer to end in 3 or like 1? Why pointers don't end in 1?
You could tag pointers from the other side where the virtual memory sort of space is also not as big as to use all 64 bits. Like
that's also possible, yes.
Right? Like you're never actually going to use like all of this memory space. So yeah, tagged pointers. What next?
Okay, so those tag pointers. So basically, the summary of this long conversation between these two stupid people. Like the idea is that we have 3 bits per pointer that are free. So we use those 3 bits to put a bunch of bullshit in every pointer. So those previous and next pointers that form the double linked list, well, now they have, every one of them have 3 extra bits. And depending on the stage of where we are, those bits are used for different things. Like for instance, like the previous pointer stores flags for collection state and finalization status. So it tells you there is a bit that says, has this object been already finalized? So it's like, that's a way we skip basically having a boolean that says, are you finalized or not? Or like, we said we will run the collection algorithm that we are going to describe in a second. That's where we store if the object have been visited, right? Like that visited, yes. So we use one of these things, right. Which makes everything very annoying because every time you actually want the pointer, you need to remove those bits. So you cannot just get the pointer anymore. You need to be aware that there's a fat pointer. So you cannot just pass the pointer around. You need to remove the bits.
That's
because
true.
Otherwise shit will be very confused or even crash.
Yeah, but before we get to the cycle detection process, what is the idea behind the doubly linked list? So who puts the next and previous fields in a Pi object? If I create a new Pi object, who makes it happen that GC next and GC prev are set? Well, and like, why is that a thing? Why do we need this double linked list?
Well, I mean, technically, because that's a very good question. Actually, it looks like he's prepared and all. Like, but it's not even on our script. So it was a genuinely good question. So in theory, the reason we need a double linked list is because we need to basically know all the objects that the GC tracks, right? So that's
yeah.
Well, but then you will say, well, there is many other ways to do it.
You can mark and sweep them. Yes,
right,
sure.
Right. The other reason is a double linked list and not like a vector or something is because you need to add and remove objects for arbitrary points in the list, right? When you destroy an object, like you need to remove it from the collection and that will happen at an arbitrary point. So if it's a list, then it's kind of annoying because like if you treat it as a normal list, then you need to remove all the objects all the time. So it's ON. And like even if you leave a hole, it's kind of really annoying. So the double linked list is theoretically the asymptotically best performing data structure. But in at least CPython before the no-GILS version of CPython,
yes.
We used to this gives you the possibility of having separate double linked lists because who tells you that the next and previous pointer needs to point to the same list? They can point to different lists. Ooh. Actually, an object can be in a list by itself. Wow. It can point to itself. That's how you know that you finished the list. Very cool, very cool. So we use this for an optimization. We're going to talk in a second, well, more than minutes. That is called generations. Generations. Wow, very smart. So Python is a generational, or used to be, a generational garbage collector. Okay, but I know this sounds very confusing, but if you're listening to this and say, these dudes sounds very confusing, I should stop the podcast now. No, it's very easy. You just need to continue thinking. It's just a list. It's a double-linked list, like, when in my interview, someone will ask me to remove, in CPYTHON. Now, you see, like all the people saying, like, when's the last time I used a double-linked list? Here. You will use it here. Do you want to do that? Here it is. The double-linked list is here with the pointers. And also, they have bits now.
Yes.
So harder. Much harder. Okay, but it's just a list, right? So let's imagine there is only one for now, just one.
Yeah.
And then you have all the objects like pointing to each other, like one object pointing to the next and the next and the next, and it just circles back. So you can both go in both directions because it's useful.
It's doubly linked.
It's double. Yes, that's the key. And okay, so the objective of the cycle collector is to find cycles. That is basically what is a cycle here. It's a group of objects. Like they are very fancy words here, like transitive closure and shit. But like let's simplify all that mambo jumbo and call it cycles. So cycles are a bunch of like objects that point to themselves, but they are not reachable from outside their own little group of objects, right? They're having a party in a different room, and nobody can reach these people. They are very exclusive. What we do with this to exclusive objects, Gukesh, what we do?
We collect them.
We collect them. Just. That's an euphemism.
Free them.
Just like the highest sticks. Whoops! Who said that? Like, okay. Sorry, Carl. Okay. Cool. So the whole point of this garbage collector is just find these cycles and then destroy it. Like it's an interview question. It's kind of cool, except that now this is C99 and you have linked list. Oh no. So what is the algorithm, Gukesh, that will tell you the cycles? Like classic algorithm to detect cycles. How will you do it if I ask you like an interview question?
Well, so you go through this doubly linked list and then you find yourself back at the same object, right? So
but how is called? Do you know the name of the algorithm?
no.
It's called Floyd's cycle finding algorithm.
What?
Floyd's cycle finding algorithm.
Oh, Floyd.
It's the tortoise and hare algorithm. Like
cool.
You have 2 pointers and one pointer goes faster than the other, and like the one is like a multiple of the other. Then the other will like go around the list, and it will meet the first one, so you will know it's a cycle.
I see.
Wow, very cool. And you can use it as a graph. Well, anyway, we don't use that shit. Why not? Because there is a very beautiful thing. This is genius. When I learn about this, I say, wow, this is fucking fantastic. It's genius. It's a property of like this fucking system of reference counting that emerges. Like if you look it close enough, it's not super surprising, but like you have not looked it close enough, so like let's pretend it's super surprising. Turns out that you have the number of references, because you're also using reference count, that is already almost enough to find all the cycles. Why? Because the number of reference tells you how many pointers the object has in the graph pointing to itself. Like if I have 6 people pointing to myself, and you can use this number and just the collection of objects to find the cycles. And this is the genius. This is the genius idea. This is fantastic. It's fantastic. You just need breadth first search. That's everything you need. Breadth first search over the graph. And the breadth first search, what it will do is that you grab every object and then you basically undo the reference counting. So you say, hey, here is an object. And then you grab the object and then you say, who do you point to? So you need a way to know like all the stuff that is inside the object. So that's why we need a specific function called
traverse.
TP traversal. Yes. So TP traversal is a function that you need to implement in C that everyone gets wrong. Yes, everyone gets wrong because like you need to do a bunch of like, it needs to be recursive and whatever. There is a bunch of macros like visit and whatnot. But basically this is a way to ask an object and say, hey, who do you point to? Like, so for instance, a list will point to all the objects in the list, right? Very simple. A dictionary will point to both the keys and the values. And a normal object will point to the dictionary, and who knows what Mark Shannon has in store for that. But that's the idea. And then you go and just grab the object, grab every object that you have visited, and then you call recursively the visit function on itself. And depending on the point of the algorithm, you will do different things every time you visit an object. So for instance, regarding the reference count, the idea here is that if you go object by object, so you use this traversal like thing to do the breadth first search, and then you subtract the reference counting, so basically every time you find an object, you remove one, then when you like look at all the collection of objects, only the objects that are only reachable from themselves will have a reference count of 0. Imagine, for instance, that you live outside my house, right?
Yes.
So I'm not going to count you because like we don't want Lucas Langer now. Sorry, Lucas, you're excluded from my house now. Oh no! And then I have a bunch of friends like here. Okay, and I point to my friends. So let's visit Pablo. Okay, so Pablo has like he points to his cat. And maybe like I don't know, like a sleep token, for instance. Like I point to sleep token. That's how it works. And then we are in a cycle because we are popular here. So my cat points to me and a sleep token, and a sleep token points to me and my cat. Like we are all together here. So when you visit me, then you go and they say, oh, I point to my cat and a sleep token. So you subtract 1 and 1 from them. So they pass to have 3 to have 2. And then you visit the cat, and then the cat points to me and a sleep token. So you subtract a sleep token 1 that leaves a sleep token with only 1, and then me with 2. And then you visit a sleep token, and a sleep token subtract 1 from everyone. So we all reach 0. And this is the way we know nobody outside the house points to us. Because if it turns out that we regain our friendship, you will point to me. So I will not have 3, I will have 4. And because nobody is visiting you, because you are outside the house, then I will never reach 0, because you are pointing for me from outside. So when we look at all the objects in my house, I will have 1 because someone else is pointing to me from the outside. That's the idea. Is the idea. And you can do this genius cycle detection algorithm only because you have the numbers of references.
Right.
Because otherwise you will need to do this mark and sweep business, like it's super complicated shit. But this is almost like the mark has already been done, kind of. Like not really, but like, you can use these like numbers, because the moment you reach 0, like basically visiting all the objects inside, then you know that those objects only refers to themselves inside the collection that you're looking to.
Okay. But that means that you need to have some, like Pablo's house, which is this sort of candidate set that you're looking at.
Yes.
There has to be an inside and an outside.
Yes, exactly.
So how do you know what's inside and what's outside?
Well, I mean, it depends, right? Like that's where the fancy words come in. But in theory, you treat them like generations. That's one thing. And the other thing, outside here can either be objects that have references that are alive. So for instance, what things are alive, are keeping objects alive? One thing is the roots. Like for instance, the roots are sys modules. Like those
modules, yes.
Yes, so modules have references to stuff. And like those are never lost. So like the module just exists, right? It technically exists in sys modules, and sys modules is just held by the interpreter. Like there's no way to unhold sys modules, right? Other possibility that keeps object alive is the stack. Like if you are executing a Python function, then the stack of the frame of the function holds the variables, because otherwise they will go away. Like if you have a local that is a list, well, something needs to keep that local alive. So that is the stack. But this is the important thing. You don't need to know who these guys are, because you just need to know that someone says that it holds the object. And this is the beauty of reference count. You can get it wrong, obviously, and then you leak. But like if you increase the reference count, because you just go and say, I increase the reference count, then I am a root now. I am a holder, but I don't need to register myself anywhere. Like I don't need to be an object on a graph.
It's implicit.
Right. Exactly. I don't need to be an object on a graph. Like it could be like you don't need to put the object anywhere. That's the point, right? To keep it alive. Right. So you just increase the reference count, and suddenly, boop, you are in charge of that number now. So you are technically an owner, but you don't need to be held by something else. Like in mark and sweep systems like Java, well, I mean, this is very complicated, so this is an oversimplification, but like in most of these systems, you have something called the roots. And the roots are normally explicit. Like those are like the things that hold the entire tree, right? And those never go away until you destroy the VM or whatever. But those are explicit. Like you can always say, and you normally, to find all the objects that are alive, you start from the roots. That's the way you will find all the possible graphs and all the objects.
And then you use TP traverse on essentially everything, and that's reachable.
Right.
Everything else that you can get to through GC next and GC prev,
yes,
but that's not reachable, that's unreachable.
Exactly.
So that's how you know.
Exactly. So we cannot do mark and sweep, like kind of, but instead the mark is basically reference count base. So basically we visit every object on the list, and then we decrease the reference count of every object that we need to copy it, obviously, because this is as a calculation. So when we enter the GC, there is 2 copies of the reference count, the real one that we don't touch, and then the GC one that we are trying to use to calculate. So we subtract the copy. We don't really change the real value.
Because if it turns out that like, okay, you're not collecting it yet, you don't want to destroy it.
Exactly. So first we do this like visit, and then we decrease this copy reference count. And then at that point we don't, because it's the copy, we don't destroy anything because nothing really reaches 0. We are using this extra copy. So nothing really is destroyed when we reach 0. And then we look at all the objects, and then we grab all the objects that have 0 reference count, and that is garbage. And then we do a very complicated algorithm that we are going to simplify for a second, which is going one by one and destroying them.
Yeah, because you need to know who you can start with.
Exactly. And this is the beautiful thing. How do we destroy the objects? Do we manually say, destroy? No, how we destroy them?
Well, we essentially just use the regular thing, which is just to set references at 0.
But how do we set the reference at 0? Okay, we just change the number and say 0.
Well, like, so first we finalize the objects, right? So like, we call the TP-del, we call it TP finalize.
That's the underscore del, right? Like that you can override in Python.
Yeah. Yes, and then what? Like
then we have another API of the GC. Because we don't want to go to the object and say, now you're dead. Like that is kind of annoying because like what happens if the object like has some like that's too complicated. So like the way we handle this is trying to do what you just described, which is use the regular thing. But the problem is that these objects are in a cycle. So going back to my example with my cat and sleep token or whatever, like every one of us has 3 references.
So you need to break the link, right?
We break the links, and what is the function called?
TP clear.
TP clear. Exactly. It's like the clear method on a list. For instance, in the list, TP clear calls clear. And that basically goes and asks the object, hey, dude, break all your references. Like just remove the references. So the list just clears itself.
Yeah.
Like removes all the objects. Like a dictionary will remove keys and values, etc. Naturally. And because you are asking all the objects to break all the links, then the objects will naturally fall at 0 in some order. What order? A lot of people like to know the order, but we won't reveal that answer because it's unspecified.
Yeah, we don't know either, but like what can happen is that you start finalizing something, right? And then there's this weird sort of word, but it's very common where it's where there's resurrection.
Right.
So something that you were just about to delete cannot be deleted. So how can an object be resurrected? Like how can that happen?
Well, I imagine that you have a class and then you implement _del, so _del. That is called when your object reaches 0. Reference count, like the badly called destructors. Not technically the destructor is called TP-dialog. So different thing. It's called the finalizer. And then you're supposed to not do anything there, but like people still do it because of course, particularly Async.io does a lot of shit there. By the way, very easy way to get deadlocks if you do stuff on that method. Anyway, so there, you can just store a reference to itself again. So for instance, imagine you have a list called Gukes-Langas-Trash.
Yeah.
And then when the del is called, you append yourself to Gukes-Langas-Trash. Now, you cannot be deleted because there is a reference from outside that points to you. So, meow, meow, meow. And this is one of the reasons, by the way, we cannot just grab a gun and like kill those objects because like after we call the finalizers, then like they may be alive. So yeah, that's bad. No bueno. It used to be that it was a bug, by the way, that like the GC never clear these objects if they keep resurrecting. And the reason is because thanks to pep something from and to ambitrue, now we have a system in which objects can only be resurrected once. So the finalizer is only called once. This means, by the way, trivia: if you resurrect an object, it doesn't the del doesn't get called again when it dies. It's only called once.
Oh.
Which, by the way, is also not guaranteed to be called. Oh, how is that possible? So the del is not guaranteed to be called. That's why you shouldn't use it as a destructor.
Yes. So that pep is pep 442, called safe object finalization.
Yes. And we abuse one of these pointers to basically store a bit that tells you if the object has been already finalized. And if it's finalized, the second time it's finalized, then we don't call anything. Because otherwise it will keep resurrecting itself. No bueno.
Yeah, but what can happen is if you have a dunder-del and it just doesn't put your object anywhere, but it references other objects, right? So it just essentially just calls some attribute, I don't know, maybe some module level, other module, or some global variable, and it does things to it. Sometimes those things are already also destroyed. They're just not there.
Right.
So finalizers don't always succeed.
Well. No, but this is important because this is the different stages. First, we identify the garbage.
Yes.
Then we finalize the garbage. But the finalizers are called at a stage when we have not destroyed anything. We have finalized shit, but not destroyed. What does this mean? It means that you will never crash, but it's possible that when you access an object, you get none.
Yes.
Right? So you try to access something, and then instead of your database connection, there is none. But you wouldn't crash when you try to access the database field, but if the database field have been already finalized or clean or whatever it is that you do in your finalizers, then that may be gone.
Yes.
But yes, like in theory we don't crash but it will be horrendous if we really delete objects at that stage, because then like you're trying to access something and we have actually deleted it, like real is not even in memory. So now what do you do? Like you're going to access a bullshit pointer. So we do that at the end. So first we call all the finalizers, and when we have called all the finalizers, we look at the stuff that has been resurrected, we move it away, and then we grab the stuff that has not been resurrected, and then we call the clear method on it, and that starts like destroying them until there is nothing left.
Right.
Yes. So that's the basic idea, and it's full of bullshit because as you can hint, like you're getting nervous, like listening to this, like, oh Jesus, like these people are telling me that it's safe, but like things are getting destroyed and like things can affect other things. So yes, this is very delicate, very delicate. It's really
It is delicate. The thing that I'm referencing is that during your application's runtime, you might have cycles that are never collected because they are in fact referenced from outside, like from a Python module. But when you're shutting down an interpreter, that's a little different because at some point there can be cycles that are now in fact unreachable, and you can now start finalizing them and whatnot. But at this interpreter shutdown stage, things can no longer be like fully ready for the finalizer to access, and dunder-del can actually hit things that were already cleaned up during interpreter shutdown. That doesn't happen often, but every now and again, like you will have a situation where you have to reorder operations because otherwise, your finalizer is hitting modules that no longer exist.
And there is a trick to avoid this. Do you know the trick?
Yeah. What's the trick?
The trick is adding the module you need at finalization. Let's say you print. The print is the classic one because if the interpreter is finalized, it may be that the sys.standard output is gone. So you cannot print anymore because you don't have access to the standard stream.
Exactly right, yeah.
Right. So how do you do this? Well, you make sys.standard output or all your dependencies, like the sys module, for instance, as a keyword, as a default argument of the del method. So you do def dunder-del, and normally that takes self and that's it, but you can take self and an extra parameter that is never used, but it's called mySys, and it defaults to sys.standard output or something like that, and then you use it. And because it's in the function, then the function cannot be called if the function has been destroyed. So when you're called, the function exists, and if the function exists, the defaults exist, and therefore the module has not been destroyed yet. Wow.
Yeah, that's exactly right. Like I've done this like in March to solve one of the interpreter shutdown crashes, like exactly like what you said, just by setting a keyword argument with the value that I want to have access to always.
Right. The key of all this dance, the beauty of this linked list bullshit is that also you don't require additional memory to hold anything here, because normally when you implement this traversal bullshit, like you normally need like a queue for the breadth first search and blah blah blah. But like here you can all this idea of like objects that are going to get deleted, objects that are garbage, objects that are not garbage, generations. All of this can be different linked lists, and you don't need to actually allocate space for them. You can just link the objects in different ways. And those are the implicit lists, but you don't need the extra space. That is super beautiful. because you can start linking the objects in a different way to separate the objects that are reachable from the objects that are not reachable. And if you look at the actual implementation, which I refactor entirely in Python 3.8, I just redo the entire GC module. Just like that was very cool to do, very tricky. So the new functions that I created basically separate all these different stages, so you can see. And if you go to the function that actually does the breadth first search, you will see that it's not clear what is going on, because it's moving constantly objects between two linked lists. Right, the unreachable linked list and the reachable linked list. Yes, and that's the breadth first search. It's a C version of one of my favorite breadth first search strategies in Python. You know which one?
No.
It's really not great because it uses a stupid amount of memory, so it's not efficient in that sense. But it's really elegant. Like, let's say you have like a list, right? And then every list is a graph, right? So you have all the items of a graph in a list, right? And then every object points to other objects and blah, blah, blah. How do you do breadth first search? Well, normally you will have a queue, and then you say, okay, I will put like the elements on the queue, and you put from the queue, and blah, 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 right?
Right.
Check this out. You do for object in objects, for edge in object, and then how do you schedule the visiting? You schedule the visiting by appending to the list. Exquisite.
Yeah.
And then you say, wow, Pablo, is this a thing? You can append to the list while you are iterating over the list? Yes, you can. You can. That's the beauty of it. You can append to the list while visiting to it. And this is the fucking magic, because you are like the pointers are preserved. As CPython is iterating over the list, you keep appending to the right of the list, and this is basically preserving the order of traversal. So you are implementing the queue using the list, but because you're appending from the other side, you don't need to like pop and shit. Like, so it's beautiful. The only problem is that the queue never just rings. So like you are storing the entire graph in that list, right? Instead of just
so it cannot be used for like indefinite.
Well, in Python it's a stupid idea because the list will grow forever. But in C, with the linked list, you don't. So the C version is this idea. Like you keep appending to the right part of the double linked list at the end, and that effectively is a breadth first search. It's super elegant because you don't need to like, you know, put the queue, so you get from the queue like blah 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 blah, like super quick breadth first search, exquisite, and is based on the fact that you can append to the list while you're iterating over the list. You cannot do that to what other data structure? This is not possible to all data structures. Which is the famous data structure you cannot modify while you iterate over it? Well,
you cannot modify any sequences, any dictionaries.
Well, sequences, yes, no, because the list you can.
No, like you cannot delete from it. Like then that
you cannot delete from it. You can append. Yes.
Yeah.
Exactly. So dictionaries you can, because like the order is basically different, right?
I didn't know that there are any mutable ones that you can safely like remove things from. Probably not, right? Like
anything that is that has random access and is order, like because you just keep moving the pointer.
Yeah.
Right. Technically, you can iterate in C over a tuple and append to the tuple, which, you know, there is a secret function called pytuple resize and blah blah blah. But like you know, like that gets you to sec faults immediately, because when you resize, the pointer gets bullshit. Anyway, that is called iterator invalidation in C++. Very very common problem. But in Python we handle kind of that for list. Anyway,
okay. But like just getting this back to like the garbage collection thing. So we do this, right? So we have this breadth first search to have like, okay, this is all unreachable. And then we actually go and decrease the virtual, let's call them, references so that we reach 0. And we know, okay, that's actually garbage. And then we do this dance with TP finalize. Oh, TP del first, like we still support that. Well, that's weird. And then finally we just do TP clear. Cool. So all of this doesn't actually touch on any word that starts with gen and ends with Asians. Like there's no generations there. So why would you need them? Like why do we need to complicate this further? This already sounds complicated. So what's the problem? Why do we want to have multiple generations, and how do they work?
Well, I mean, this is the same reason, like doing this with the full mark and sweep with all the objects is bad, because there is a lot of objects. So iterating, like the key here is that normally you have a lot of objects that will not really need the GC, right? Like the idea here is that you will have a lot of cycles, but most objects are reference counted, right? Or that's the main hypothesis, which like, some people are like, particularly Sam Gross will like to discuss with me about if it's true or not, but like, let's assume it's true. It sounds reasonable that most objects will not be needed the GC because eventually you will destroy the cycles yourself, or because there is no cycles at all, right? Okay, so for those objects, you don't need to do really any GC at all, but you still need to pay for the traversal. So when you're doing this dance of like finding the objects and marking them and blah, 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 the time you spend on the GC grows with the number of objects that are alive that participate in the GC.
In the application.
Right.
But TP traverse, is that related to GC prev and GC next? Like,
no,
that actually is not just things that the garbage collector sees. That's any object that is in the application. That might include things that are not part of a cycle.
Yeah, but when you end an object that doesn't participate in the GC, you stop there. But you still reach it, but like, but that's
you
it.
need to reach it. Yes.
Right, yes. So the idea here, but that object is not on in the double linked list, right? It's reachable from it.
Yes, it's not on the Yes, it's not there, but TP traverse also is still going to tell you all of them.
Just to highlight what you say, you can have a list with 6 million strings, right? And you still need to touch the 6 million strings.
Exactly.
So
that's the thing.
Yeah, that's bad. Strings don't participate in GC because they are not containers.
Because they are immutable, yes. They're not containers.
Immutable doesn't, like there is some discussion if you really need GC TP clear and whatnot, and there is some dance, like if you are immutable, you may need it, like tuples still are visited because you can be immutable and point to mutable objects, like you can have a list in a tuple.
That's true.
Right, so like technically you don't need to participate in the GC only if you are immutable and you cannot contain shit.
That's good insight. Okay.
Right, and you say, well, what about if you are mutable but you don't contain shit? Well, it depends. Okay, so the key here is that you don't want to visit all the objects all the time. That's annoying. So there is this fancy wording called the weak generational hypothesis, and people talk about this like there is the strong generational hypothesis, but I have never listened to anyone saying the strong generational hypothesis. So like there is only this thing, the weak generational hypothesis, and what this basically says is that most objects die young, like rock and roll stars. So the idea is that Python creates a lot of temporary objects and then they kill it. This happens all the time you call function, right? Because the locals are temporary objects, right? You call a function and then the objects are gone and bada boom, dim boom. And those objects normally are also cleaned by reference count, so they don't need the GC. So the idea is that because these objects will basically die quickly, if you're triggering the GC a lot and you're visiting all the objects, you're visiting a lot of objects that are going to die anyway very soon. So like, where are you spending the time? So really, the idea of the generation is that instead of like having like all the objects in a single list, you have several lists. I mean, CPython has 3, but by the way, it has a define macro where you can like have arbitrary number of lists. Not that anyone uses it, but like it's there if you want to.
Yeah, you can.
Yes. So, which by the way, it turns out it was a very bad idea because like now, spoiler, we use only one in free threaded. But anyway, well, I think right now even we use only one. Well, anyway, so the idea here is that the first list is called the first generation or the young generation, and the idea there is that you put all the objects there at the beginning when they are created, and when you do like a run of the GC, you only visit the objects in that generation, and everything that survives, basically everything that is reachable still that it has not been deleted, you instead of leaving it in the same list, you put it in another list which we call the middle generation.
Yeah,
and when that middle generation is basically like traverse, and like everything that survives is pushed to the next generation, which we call the old generation. And the idea here is that you visit less the older generations.
Yes, you do them less often because you sort of suspect that the old generation is not going to be changing that often, so you're not going to be able to clean the garbage that wasn't able to be cleaned until reaching the old threshold.
Exactly. And also this gives us a very interesting thing that many people don't know, by the way, which is that when the GC runs, like when do you run the GC? I mean, you can trigger it yourself, but when it runs naturally?
When there is no Python evaluation. So in the loop for Python evaluation, you have the eval breaker.
Well, that's a change I did in 3.10, I think. So before, yes. But when that's where it runs. but when it runs. Before it run immediately, now it's scheduled to run in the eval breaker. But like who triggers who schedules the GC? Like when is it scheduled? What is the condition to decide now we should run the GC?
I don't know actually.
It's the number of objects in the generation.
I see.
So every generation has a size. So when you create objects, you append to the first generation, and when you promote that generation to the next one, then the second grows. So there is some numbers that you can access by calling gc.getThreshold.
Ooh.
There is 3 numbers if there is 3 generations, 5 if there is 5, 1 if there is 1. If there is 1, it's a bit more tricky, but let's say that you have 3. So that is the limit of objects that exist in the generation before the GC triggers. So if you, for instance, have the first generations and the limit is 1000, when you surpass that 1000, then the GC will trigger. And
I see.
And that's it. The last generation is much trickier.
But what does that mean? Does that mean that if my generation still contains objects kind of more than the threshold, then it'll trigger every time?
Well, what do you mean? Like, I mean,
so for every eval breaker, you're gonna still do the collection for that particular generation because the threshold is still
right. The first thing that happens is that the GC sees what is the oldest generation that can be collected. So, for instance, if you have the second generation and the first generation full, or even if the second generation is full, what it does is that it merges that generation with every previous one, and that collects the collection in one go. So if you have for instance, the first generation is full, when you basically collect it, and then everything that is there is promoted to the second generation, so now it's not full anymore, it's empty. So until you fill it again, it's not going to be collected again. But if the second generation is collected, it's going to be joined with the first, and then the whole group is going to be collected. That makes sense? That makes sense?
Yes.
So after the collection, is the generations are empty.
But the things that were not actually collected because they were still reachable, right? Then those finally end up in Gen 2.
In the next one. So 1 goes to 2, 2 goes to 3. Right?
Oh, okay. I thought like of Gen 0, 1, and 2. So
sorry. 0 goes to 1, 1 goes to 2.
Like, yeah, that's the last one. So it's always there. So if there are a ton of objects in that old generation, like, is generation triggered by only the younger generations?
No. So the last generation is special. And it used to be the case that we do the stupid thing, like long ago, when you basically every time you add more objects, you trigger it. But that will mean that you're triggering it constantly because as soon there is no more generations to move, so that generation can only grow.
Exactly right, yeah.
But normally, if everything is reachable in the last generation and you don't destroy anything, you will keep like triggering it again and again and again. So all collections will be the last collection, right? So the last generation trigger, which is it uses the numbering GetThreshold, but it's a bit more complicated. It basically has a formula, not super complex, but it has a formula that takes into account how many objects are you moving. So is the new object that have been moved from the last time divided by the staff, and like there is some number there that adjusts it, and like it was a big change that was done shortly after the GC was introduced. But it's just a bit more tricky, and the idea is that obviously you don't want to keep triggering it again and again and again.
Yep.
Makes sense?
Yes.
All right. We also have another optimization which we do to a bunch of fields, which is delayed untracking. So what is delayed untracking?
Delayed untracking?
You know it?
Never heard of it.
Let's say you create a dictionary. The dictionary starts being empty. Does it make sense to collect it?
No.
Because it's empty.
Yeah.
Right. So objects that are participating in the GC have a field that you can deactivate or activate that tells it the object, even if it's a GC object, if it's being tracked or not. You can opt out of the GC if you want, even if you are a GC object, right? Why you will do this? Well, you will do it for many reasons. Maybe you don't want to do it. This can only be done from C, by the way. You cannot do this from Python for reasons. But when the dictionary is empty, it doesn't make sense to traverse it because it's costly, right?
Yes.
So some objects like especially things like tuples that only contain immutable objects, the empty dictionaries, things like this.
Oh, so that's is tracked.
Yes.
Okay, I didn't know it's called delayed untracking, because how is it delayed?
Well, delayed untracking is delayed because you track it later. So delayed untracking uses the is track or is untrack. But the dictionary, when you create the dictionary, it participates in the GC, but it's not immediately tracked. So the tracking is set to 0.
So the response is tracked false for a while,
Exactly.
and then when it's not empty,
and only when you add to
true.
it, then it says now I'm track. The dictionary
Okay.
is kind of obvious because like you will say, well, the first time you put something, then it's track. But the interesting one that is a bit more like sophisticated is tuples. So tuples that only have like immutable objects, like transitively speaking, those are on track. But like when you add something that is mutable, or when you create like, and this is tricky because like you can have a tuple with an empty dictionary, and then the empty dictionary is not tracked, but then you put something and now it's tracked. So like there is conditions here, obviously, but like a lot of these objects are tracked later. So they have logic internally that will activate tracking when it makes sense to track. Obviously, if there is a bug there, then you will leak, right?
Yeah, that makes sense to me.
Right. So that is Mark Shannon has changed the hell out of that recently, by the way, because like that code is really complicated. But in general, that's another optimization to reduce the number of objects that like you basically traverse. And then there is the big enemy of the garbage collector, which is the last thing that we want to mention in this part. Which is the big enemy of the garbage collector cookies. Is the source of mostly all the bugs in the GC. Weak references.
Oh,
Those are evil. Those are evil. What is a weak reference, Gukesh? Tell us what is a weak reference.
A weak reference is a reference that will avoid creating a cycle. So it's a reference where if it is the only reference to an object, it'll let go of this object. It'll TP clear, right? It'll just decide, okay, I don't want you anymore. So those are references for things that are optimizations, like caches, like things that it's nice to have a reference to a thing, but it's not a tragedy to your program if you lose it, even if that thing still exists, right? So weak references are sort of references where you know that you're not the true owner of that object. You're only holding on to a reference for some caching purposes, for some purposes of faster traversal to be able to get to an object because it's convenient for presentation or whatever. So a weak reference allows you to not create a cycle and with that to actually avoid the entire garbage cycle. So I don't understand how that would be the enemy of the garbage collector.
Well,
isn't the entire point to avoid the garbage collector?
But yes, but you're missing one key detail. It's like, what other feature weak reference do have?
Right.
They have callbacks.
Oh, okay. So you can have a callback when the reference was cleared.
Right. And then isn't that a bit tricky? Because if you get a callback when the object is destroyed,
yes.
Like where is the object? Like what happens if that callback reaches the object?
Oh, there's no object anymore, maybe.
Well, or we can resurrect it. Or what happens if that object has more weak references? So you see, like the graph of weak references is really, really tricky. Because those callback can either access the object being destroyed, if you call it afterwards, or it could reach other object that has other weak references and like fuck up the order and resurrect shit. Like that is really bad. So you don't want to allow this, right? Because then the callbacks are not that true. Like the object has not been destroyed, right? So like those weak references are really, really, really tricky. The way we work with them is that basically as we are like finding all the objects that we need to destroy, when it's the time to destroy shit, we basically find the set of all the weak references that are unreachable, and then we set all the objects to none. That's the way we avoid the weak reference finding shit.
Oh,
and then we queue them from destroying. So this is the key. We first run all the callbacks in a way that the callbacks cannot reach the objects. And only when that is done, then we actually destroy the objects. So the callback never can reach either calling gc.getObjects and shit like that. Like they can never reach objects that are being destroyed and resurrected and things like that. So that is tricky.
That's fascinating. I never knew that.
So the other important thing is that if the weak reference and the object itself are in a cycle, so you can have the weak reference and the object to be destroyed in a cycle.
Yeah.
Right? Because like, why not? And so those, if we know that we are going to destroy the weak reference and the object, so both are in the same cycle, we call shit. Okay, we lost the Apple the explicit category.
Oh, we did that like 55 minutes ago.
So we that's the key. So because if you're going to delete the reference, because the order is unspecified, this is the beauty of having unspecified ordering, we can pretend that we destroy the reference count before we destroy the object. So the reference count, the weak reference. So because we destroy the weak reference before we destroy the object, we never need to call the callback because the weak reference was gone. So there is no more callback. So if the weak reference is in the same cycle, because it will be a fucking nightmare to basically like call things in the appropriate order and respect things, we just pretend that we destroyed the weak reference before and we never call the callback. That's a way to avoid a lot of bugs. Yes, in general, as you can, as Neil Schumacher knows, like most problems with the GC are in the like weak reference problem. Like if you go to the code, you will see that the biggest comments are about like weak references.
I thought that you were transitioning to talking about free threading because that sounds like something that complicates lives of garbage collectors and everything, because you need to essentially stop the world to do this entire process of both linked lists and everything, and that's not scaling very well. So we have a different one for free threading.
Yeah, free threading does things a bit easier for some things and harder for another. This is also changing a bit, but like most of that is in Sam's PEP for free threaded. The idea here is that the memory layout is different. So instead of like all these fields, like we keep using the trick of reusing stuff for different reasons. So we use our 1 byte for the like the GC bits field that are in the GC track stack. So the header now has like a different field called GC bits, and we put all the stuff on there. And then we abuse the thread ID that we need to store in the object for like the bias reference counting and all that stuff, which we abuse that field to basically store the local reference count over there. So the header is slightly different because it reuses a lot of the free-threaded data for different purposes. And the idea here is that you want to reuse it because you are going to be paid for this extra size for every object. So if you are using 1 byte in your whole program, that's 1 byte times the number of objects. So you really want to keep all this data to the minimum. By the way, shout out to Inada-san. That was the person who started to reuse all these fields. I use fat pointers and whatnot to reduce the object header, and that make CPython use a lot less memory because of this. It's more complicated. But the thing that is easier in the free threaded world is that there is no more linked list, or at least not constantly. We talked about this in the past. We use memalloc, and memalloc is a different allocator from Microsoft, and memalloc has the capability to basically give you the actual location of the object. So instead of like going through the linked list and visiting all the objects, we go through to the memory. We call like this a specific pool. I think it's called a heap in the memalloc terminology, and then you go to where the objects live, and then you start visiting all the different parts of the memory that was held by the allocator. It's just that now you need to deal with holes in the allocator because the allocator may have regions of the memory that is not used, or it has been used in the past and now it's not. So you need to like skip over those. So the complexity is less because now it's not the number of objects that are alive; it's the size of the heap, right? Because like, you don't know, like if you have like a huge amount of memory that is not used, you still need to pass through it because unless you use skip lists and stuff, which I don't know if we use. But that is easier technically because you don't need to handle lists and shit. Unfortunately, most of the APIs assume...
But yeah, if you don't have lists, that means you have to look at everything every time though. So does that mean there are no generations?
There are no generations anymore. There is some tricks to make this like less crazy, and we use the complicated formula for the last generation in a different way. But yes, no more generations anymore. And actually, it's even harder because like there is some APIs from the collector. For instance, the collector has a module in Python called the GC module, so you can import GC. And among other functionality here, you can get all the objects in all the generations, in this case, all the objects because there is only one. Or you can get all the objects that are being referenced by some other object using the traversal, right?
Yeah.
So to keep those functions to keep working with the same API, like the free-threaded GC needs to recreate the linked list in some of these calls. So it's really annoying.
That's costly, yeah.
Yes, that's really annoying. That's why that is a bit more costly. That keeps changing, but the original implementation, and I think we still do it, recreates the linked list for giving to you the list of objects or to do the traversals and whatnot.
Yeah, so you mentioned local and non-local reference counts, but we didn't really explain the bird's eye view of deferred reference counting. So how about we do that so we know what we're talking about, since we didn't really cover deferred reference counting in the reference counting episode.
So what happens with deferred reference counting, Lukas?
Man, we actually have 3 kinds of reference counting for free-threaded builds. What you need to understand is that in the world of free threading, even counting is complicated, right? So for many operations, you will be able to use atomic operations, which guarantee correctness. They might not be super quick, but they will be correct. But in some cases, you will have to use locking, which hinders scalability, hinders performance, and then you can get into those deadlocking situations that you want to avoid. So we have actually 3 strategies to avoid reference counting contention. The most used one is a biased ref counting, actually.
Right.
And this one utilizes this sort of realization that most objects, as you said, they are short-lived. And when they are short-lived, that actually means they are being created and destroyed within the context of one thread. So because of this, in free-threaded builds, we have 2 ref counting fields. The local one that is only ever mutated by the owning thread,
Yes.
so by the thread that created an object.
Yes.
And then you have a shared one that is being updated by everybody else by using those atomic operations that I mentioned. And in very many cases, you can actually avoid any complexity of multi-threading because only the local field is ever being accessed. And in this case, things are as fast as they would be in just a single threaded scenario. If they're not, then the shared field is being updated. And in a very unlucky case, that's rare, but it's possible, you might actually get the shared field to get to a negative number, to a negative value. And in this case, those other threads are going to say, uh-oh, something's wrong. The ref count should never be negative. So they will use a queue to tell the owning thread that, hey, man, like you should merge the local and the shared values such that we actually figure out if this object should still be alive or not.
Exactly.
For correctness, that number should still be 0. The negative number comes from the fact that every now and again there might be a situation where there is an imbalance between increfs and decrefs between threads. Rare, but can happen. So we have support for that. So this is the case that is most often seen, where most objects mostly only ever accessed by one thread. But we have also an opposite. In some kinds of objects, some types of objects, it is extremely common for them to be accessed from multiple threads.
Right.
And in this case, the contention will be terrible. So we used deferred reference counting, which essentially means please avoid reference counts when multiple threads are executing code using that particular object. Because what's very often happening is that you are increasing a reference only because a frame is accessing some piece of data. So if it's accessing it, it's increfing. And when that frame object is destroyed, it's decrefing. So we avoid this operation for deferred reference counted objects. Those have to actually opt into deferred reference counting, and they need to be able to be garbage collected,
Right.
because they are only ever deallocated during garbage collection because of those deferred situations of reference counting. And this is because that deallocation needs to access all of the current stacks
Yes.
of all threads to figure out whether the object that we want to deallocate isn't actually being used anywhere. If it is, then we're leaving it alone. If it's not, then we can safely deallocate it. So yeah, is it simple? Not really, but it's the world of free threading. And I mentioned there's three ways. So there's also a third thing that is sort of part of deferred reference counting called per thread reference counting. So you can have some sort of the reference counting that uses unique IDs of objects where every thread maintains its own reference counting for a particular object, and then it gets combined in the end. That is particularly rare, but like we do need this for example, the reference from instances to their heap types.
Wow.
And shout out to Sam Gross, who helped me decipher all this, since the PEP actually has a very condensed sort of paragraph per topic on that, and the implementation has all those details scattered across very many files and tiny operations. And this sort of bird's eye view of what the design isn't really codified anywhere as far as I can tell. So thanks, Sam, for actually letting me pick your brain on this when I was researching for this episode.
And as a surprise, because we should move on, because this is getting too... we are going to have an extra episode. Wow. Maybe not a full one, or maybe it will. Yes. Like, why not? Why not? Maybe that can be short once and for all. About another optimization that was very recent in Python 3.13. Was almost not shipped with Python 3.13, but finally was shipped with Python 3.13, which is from our own Mark Shannon, implemented
incremental garbage collection.
Incremental garbage collection.
Yeah.
And we are going to, and that implementation is full of cool words like transitive closures and whatnot. So we will talk about that optimization later, because that is confusing to understand why it's correct. So it is correct, but like we will talk about it in another episode. Because now,
very cool.
Now it's time for what? All right. For some reason, I'm first here. You should be first, technically, because I tend to talk more. But I'm going to be first anyway. Okay. My PR of the week is a draft that I just did 1 hour ago because I wanted to have a PR. because the other PR of the week was we landed PEP 768.
And 758 as well. Since last episode.
Yes, both of them.
Yeah, both of them.
Very cool, very cool. But like, we talked about that in the last episode, so it was not cool enough.
Yes.
So I had an idea that I've been like ruminating for a while, which was to improve the error messages even more. And something that I was never like, it was like a small thing that I never managed to do, which is like typos on keywords. So instead of for, you say for, or like from, or something like that, right? We already have typos on names and things like that, and attributes like that. Those work fantastically, super popular change. But like typos on keywords is harder because the names are not syntax errors, right? Like name errors are not syntax error, and like the attribute is the same. Like it's just that you mistype something that doesn't exist, but the parser is happy with your code anyway. But keywords are a bit funky. And the reason keywords are a bit funky is because like you cannot even say, you cannot even tell the parser, like it's just illegal syntax because after for it needs to happen like a name or an expression, and then in like, and then you don't put these, like then say, maybe you are missing an expression. Like typos in keywords are much harder to handle because they appear as names, right? If you write from instead of from, that it looks like a variable called from.
The tokenizer is presenting you with a name.
And then the parser is going to say, this fucking makes no sense. And there is no way to match against it. Like, no way. You will need to basically go to every possible place in the grammar that has a keyword and then add an invalid
just
rule.
do Levenstein distance. Yes.
Yes, and then it's like it's just fucking insane. So that's like...
way too slow.
Yes, it's way too slow. So I had a revelation, and actually been trying to work with Ivona on different ideas, and I've been like trying different things. But I think I found an idea that's very cool, and I'm going to try to put it in 3.14 before we reach beta 1. Do you know the idea?
Ooh, no, I don't know yet.
Okay, listen to me.
Tell me.
Okay. So this is the key. You get a syntax error. So we know that there is a syntax error. Something went wrong.
Yes.
Okay. We know the exception has the line. Like the actual text on the line that failed. Only the line that failed, not the rest of the program. The rest of the program, by the way, is gone. Okay, so this is the idea I have. If we knew the last statement that was okay, the last statement that was okay. So that's something that I had to teach the parser to know. Like, what is the last statement that you parsed that was fine? And then we know that location. So we know the line that failed. So we can extract the text from the last statement that actually parsed from the line that failed. Okay?
Yes.
So we have that chunk of the program.
Right.
Which is probably going to be very small, right? It's not going to be fucking huge. Because we don't. What we're going to do is very expensive, so we don't want to like do this thing with the entire file. Okay, so you have that chunk, right? You tokenize the thing, right? And then you go through all the names that are in the line that failed. Okay.
Yes.
So the line that failed may have like 3 names, 6 names, and then you go name by
Levenstein
name.
Distance on that.
It uses Levenstein distance with every possible keyword, right?
Yes.
So only the ones that are really close will tell you something that is not 0, right?
Of course.
But that doesn't mean anything because like you can have a variable that is called much and it's going to say maybe it's much or something like that, right? Like that's not great. So do you know what then it tries? This is the genius part. It will grab that possible typo. It will substitute it for the keyword you think it is, and it will try to reparse it. And if it succeeds, then it's probably a typo. And that's why you don't want to do it with the entire program because you are going to try to reparse for every name. And if you use a super big program, it's going to be slow. But if you use a very tiny program...
So you need probably to have some, bail threshold where you're like, okay, I'm trying to reparse it too many times. Because I can tell you that in my time at Facebook, like there were Python files that were multi-megabyte big because they were gigantic dictionaries essentially. So if you
that's fine, no? Because that's the first optimization that I did. So there is 3 bails. There is bail based on the number of lines in the small code. There is bail on the number of names in the line. But the key here, the big optimization that I did, that's why I had to teach the parser, is that it just reparses the space from the last statement that worked to the line that failed. That is probably like 2 lines.
No, but like last statement that worked, right?
That succeeded, yes. So that's probably 2 lines.
Yeah, so like if you have like a gigantic dictionary and in the middle of it you have a syntax error, then like good luck.
Oh yeah, you start from the beginning of the dictionary. Yes.
Yeah,
yes.
That's my point.
Yeah, but it won't work because you will need to limit it, right? So it will find that the dictionary has like 600 million lines or like 600 million bytes or whatever it is, and it will not try to reparse it.
Mm-hmm.
So only for a small
that
thing.
sounds really cool. Like if we can get it to 3.14, then you're gonna have like at least one feature that you wrote for Python 3.14.
I think my name appears like 8 times on the What's New.
Yes, you're gonna be all over the What's New. That's amazing.
Yeah, it was not even a version in which I'm the release manager. Anyway, there's still a draft, and as you mentioned, it needs some love to finish it.
Currently, it's very red, but yeah, like we can probably get it to green.
Yeah. Right now, it's just rough, but like I think the idea is cool, and the draft is just to prove that it works. Has no tests and whatnot, but
my PR of the week is weird because it is sort of unrelated really to syntax highlighting that I'm working on right now.
Yeah, what it is, man. You by the way, I was listening to our last episode for reasons last time, and you had all this like explanation, like saying, oh, but you cannot be a bad person like committing this thing before last alpha because like people want to try it and like the people will compile Python just because this. What is the feature? What is the feature?
Well, so like. I did try to just use a tokenizer for syntax highlighting, and it was over 3 times faster than what the regular expressions now do. So
I wonder who recommended that.
It's like me, Łukasz Langa was wrong, and Pablo Galindo Salgado was right.
Yes.
I am now actually doing the soft keyword thing, like the mini parser thing, so that actually we do recognize them correctly. Which is why I did not actually finish that in time because I wanted to use nicely pick parser and everything so that we could, I wouldn't roll my like hand rolled parser for this because
how is Frankenstein? It's probably the same, right?
That's how I tested. So like, yes. So it is still slower than obviously no syntax highlighting, but like at this point it's like 50% slower and not like 5 times slower.
It should be, I think if we do it correctly, it should be no slower, right? Because like that token will only be tokenized once. I don't see.
Yeah, well, we can optimize this further, but at this point, this is sort of something that is landable. But like that's a thing that is not finished yet, so I did not like put the PR up yet. But related to it is that both PyRepl and the colors that we're using for colorize and whatnot, both of them are sort of spearheading modules in CPython that use type annotations internally in their own code base. And that thing allows you to first type check actually that module. There is a lot of type checked Python files in CPython's repository, but most of them are either in tools or in regression tests. Whereas PyRepl and Colorize are the first actual modules or packages that are type checked, and they're fairly strictly type annotated. And this, it turns out, creates a problem. That MyPy, the type checker that we're using, is not really expecting that you will be working on CPython. You will be developing a next version of CPython.
Right.
So it does a bunch of like things that work against this use case. One thing is that it ships with a bunch of special handling for modules like typing, types, and collections.abc. This special handling is because those modules contain types that the type checker really relies on, and they're very deeply ingrained in the implementation of the type checker. So you cannot have a program that would shadow those magic modules, because then type checking will just not work, because a lot of those types that are contained in those modules are just hard-coded in a type checker. So you cannot just have another file that is called just types.py and it's incompatible with what Python is doing. That will not type check with MyPy.
Right.
So what that means is you cannot point MyPy at the standard library, because pointing it at the standard library will mean necessarily that it's going to find all those special modules that it says, no, you cannot shadow those, because it doesn't understand that those are actually Python modules, but from the next version. And additionally, there is TypeShed, which is this external way of type annotating the standard library, and it is powerful to the extent where a lot of our implementation is dynamic enough that it would be very hard to just annotate it correctly in source code. So TypeShed allows us to have meaningful and useful annotations, but they live outside of the source code.
Right.
So those two problems end up like making it very hard for us to have a local and CI workflow where MyPy is type checking PyRepl and Colorize and hopefully other modules in the future in the standard library, because you cannot just point it at a directory. So I made something kind of evil, but also, like it works, which is to create a new directory just for MyPy. And that new directory is just somewhere in MISC, contains symlinks in Git that are relative symlinks to modules in the standard library that we know are fully type annotated and they are ready to be type checked. So from MyPy's perspective, you have only a few libraries that we're looking at,
right.
And those are not the ones that are special. Those are not those that you cannot shadow the standard library with. So type checking with that works, and in fact we are using it right now on CI. But it turns out that using symlinks in a repository has consequences. And you would expect that, consequences, because what? Like people on Windows will check out Python and they will not know how to symlink a file to a file. It turns out that actually works. It's fine. But what is not fine is that when we are releasing Python, we're releasing installers for Windows and macOS, but we're also releasing a source tarball, which is just an archive with cleaned up sources. And when you have symlinks there, that would mean that you have to also list them in the bill of materials, right? Like the software bill of materials, this SBOM. And it turns out that the SBOM isn't really designed to deal with symlinks. There is no agreed way, like what to do with symlinks.
That is kind of surprising.
That is weird, right? Yeah.
Right.
So what we did during our last release is to just decide on not including those symlinks that are for local development, mostly only and CI. And thanks to them not being there, we can just not include them in the SBOM for the source tarball. We're already removing plenty of files in the source tarball, like files that are only necessary for the Git repository configuration and for CI configuration. Like, we had Travis in the past, and now we have GitHub Actions and whatever. So all of that is removed anyway. So just removing another directory with symlinks from the source tarball, not very controversial. So we did that. But what if somebody actually gets a repository without symlinks and they want them back? So I just wrote a script to essentially have a single source of truth for those modules in the standard library are fully type checked, and we expect them to be able to both be type checked by MyPy and also to be dependencies of other stuff that you want to type check with. So those things don't require typeshed.
Maybe it's time to embed typeshed in the standard library. Who said that?
All I'm saying now, the reason why I'm sort of talking about this now is that the change itself is not really that kind of deep or interesting, but it sort of presents us with this delicate shift in core development where we're no longer sort of ruling out having type annotations in the standard library. It is still a thing where newly created libraries and functionality is not type annotated, and that's fine, I guess. But we also allow the presence of MyPy there, and we allow the presence of type annotations in new standard libraries. We're actually going to be talking about some of the improvements in that in the next section. But yeah, that was my change. That was an unexpected issue with something that I expected to have issues with, but not related to releases.
Well, for what it's worth, I like the way you resolve this finally. So I think it's the cleanest version given the problems that we have.
So I mean, I like it because that's there were two possible solutions, and I kind of advocated for the one that we have right now. Thomas was not entirely happy with having symlinks in the repository at all, so he still advocated for us to remove them and just to have some make command that would recreate them. But what that would mean is you would need to recreate those symlinks every time you change the branch in local development.
Yeah, no, it's disgusting.
That would be annoying. Or it would require you to build Python to type check the standard library, which you also don't want, because MyPy, the CI that we use for type checking, is not actually building Python. You don't have to compile Python. You can just have the Python that is already there, pointed as a standard library at tools and other directories, and just run. You just check whether the types are good.
We could technically have a make MyPy check that runs MyPy and first recreate the symlinks and then destroys the symlinks. So the symlinks are a transient thing, but I think the version that you have is more elegant.
Yes, but for a local workflow where you are in a text editor and you just hack on things and just expect them to just type check in the background, that would be annoying, because now the normal thing of just being able to run MyPy would not work. You would have to have the not normal thing of some custom
always
command.
run in all my projects. I always have a makefile and I use the makefile. I never run MyPy blah blah blah. I use make MyPy or something like that.
Most people don't even do that because they just use Pyrite or whatever else, because that's the magic. The weird directory also works with.
Did you know that
Pyrite just fine.
that used to be so common that GDB understands that. You know that you can say make inside the GDB and it runs make.
Oh, interesting.
This is very cool. Yeah, GDB is stupid.
Yeah, like I'm not saying the symlinks are for sure gonna survive, like, until 3.14 final. We might discover more fun issues with them, but for now, this is the moment in time where the main branch on Python does contain symlinks, and that's on purpose.
All right. Very cool. I hope that in the next episode you have already implemented the syntax highlighting.
Yes, like in 2 weeks, like that. Yes, that's more than likely, because like the soft keywords is
and you need
all that's left.
And you need to also account for the fact that you need to review the next PR that we have planned. Remote PDB. Who said that? Remote PDB?
Remote PDB.
Possible? Is that possible?
Yes, wow. It is vaporware in terms of PRs, but it's not vaporware in terms of proofs of concept. I tested this just yesterday, and you can, in fact, now, with the current state of the main branch, have remote PDB. It is indeed possible. Like the PDB itself doesn't do it yet, but you can make it work. So the PR is coming.
We are sprinting. Yes, it will.
Yeah, that's amazing.
I'm confident that we will have it for 3.14.
Yes, it is pretty cool.
Now it's time for
what's going on in CPYTHON.
All right, so let me start with free threading. And again, we are so late in the episode that we're going to have to be a little quick about it.
But that's...
What?
Like,
okay.
Fast. Come on.
No, that's not faster Python. That's scalable Python, free threading.
Yes.
Kumar Aditya and Peter Bierma switched C types to use free threading friendly critical sections. Before that, the library was relying on the GAL, and that was no bueno. So in particular, critical sections are now used for C-types' global state. So that's thread safe. The critical sections were added to array getters and setters. And also C-types' custom lock pointer, unlock pointer macros are now removed. So Peter even found 2 data races and fixed them during introduction of this change. So C-types should be much, much better in 3.14.
Very cool.
Neil Schemenauer switched catch warnings to use context vars. So Yuri, when we talked to him, he was like, I made those context vars, but I'm not actually using them myself now. It's like, I'm not sure whether...
Now you are.
Now he will, right? Because everybody will. Because this makes the warning filters thread safe while allowing reuse of the context between threads. Because with threads, you don't need context vars, right? You have thread locals. But the thing about thread locals is that they are always separate. They're always, isolated. So if you wanted to actually, inherit the context of a thread that your new thread started from, you couldn't use thread locals for that.
Right.
But with context vars, you can, and it's cheap. So Yuri's context vars end up being useful even in threaded context. That was an amazing thing. Yes. So sysconfig getConfig vars now returns uppercase ABI flags on Windows, and that can help differentiate free threading and debug builds from the default build, thanks to ZooHiPan. Element 3 element remove used to crash during parallel mutations, and that is no longer the case thanks to Benedict Tran.
Amazing feature.
Well, it is cool when we don't crash. Yes, right. Amazing. And as usual, Sam Gross improved many things in multi-threading. So improved multi-thread scaling, as well as avoided some ref count contention in some special cases, and fixed some data races. We don't really have time to get into all of those changes, but there is a lot of free threading activity at the moment in Python.
Right. And all is happening in parallel. Amazing. Different people do different things.
Yes.
Okay. Performance. Now let's talk about performance. Matt Page from Meta introduced load fast borrow. because it has
Because borrowing is so cool, and we always love it, and we never call it evil.
Borrow. No burrow. It's not like burrow. No, it's borrow. Okay.
Fast borrow.
It's a new opcode which is emitted by the compiler, not by the parser, because the parser doesn't emit opcode. It's stupid. So when it can be sure that the reference in the frame outlives the reference that is pushed onto by the operand stack. This makes that basically it just doesn't get the stupid reference count higher, right? Because it's borrowing. Yes. This gives a 2.7% improvement in the default build and 3% in the free threaded build. Makes sense.
Very cool.
Yeah, interesting. Okay. Yeah, makes sense to me. All right. Edit optimize the any, all, and tuple calls for generators, which now makes, according to some benchmarks, 10% improvement.
Nice.
Text wrap the dent used by everyone that has ever compiled chunks of strings now is now 2.69 times faster thanks to Adam Turner, based on a previous PR by Marius Juston.
Yeah.
Adam Turner as well optimized the import type of the stream module by 25 times. Amazing.
Yes.
By replacing template.init subclass with a descriptor. Very cool. Why a meta class is here? Who knows? But yeah, okay.
It's essentially avoiding importing regular expressions if you don't need that, because a lot of people only use the string module for the constants that are there.
But you don't know something. Now people are going to use the stream module for a lot of more things. You know why, right? Because the stream module will have a new submodule called template lib for T strings that was accepted by the string council. Those dudes, like, you cannot trust them.
Cool.
No.
That's not just dudes, though.
Okay, sorry. Those yes.
Dudes and dudettes.
Those dudes and dudettes. Apologies. Yes. I'm stupid. Don't listen to me. I'm stupid. All right. Chris Abel. I don't know how to pronounce this correctly. Able added fast path to more of the pylon from asterisk. That means all the pylon functions. It's a glob. Speaking glob. Improving the performance of those functions between 30% and 10 times. Wow, that's a fucking big range.
Yes, 10 times is for the smallest integers, but it's amazing, right?
Well, I mean, those are very common.
Yes.
Michael Drutbum, the team leader of the faster, team leader, not the manager, no? The manager of the faster CPYTHON group at Microsoft, added caching results of tuple hash, which improves the MDP benchmark, one of the ones that we use in speedofpython.org for tuples, by 86%. Amazing.
Yeah, impressive.
And Brian Booker made a small speed boost in the JIT, one of the 3 JITs that we have in the standard library, the last one to be added, by removing some unnecessary guard checks. He reminded me that I was not the first, I was the second. The first JIT was technically the one in C-types.
Very
new
cool.
features.
Yeah.
This is kind of a new thing.
Yes. There are a few that are, I think, worth mentioning. So let me start with the HTTPS one. So we now support HTTPS in http.server. This is the silly server that people mostly use during development. It says very loudly in the documentation that you should not be using that for any production purpose. However, it is pretty useful in development, and now it supports HTTPS thanks to Semyon Moros. Moreover, this is exposed in the popular command line interface to that module. So you specify the public TLS-cert path, and optionally even the private key path. And you can actually have working TLS that you can use with your browser for local development, which often behaves differently from just HTTP, which makes this pretty useful.
Amazing. Now, we have PEP 768 and PEP 758 landed, both of them. So now you can enjoy remote code execution by design, and also drop some parentheses in exceptions, but the good version of the PEP, not the bad version that everybody hated. This is the good one. Yes.
Yes, very nice that this is landed now. Yeah, like very happy.
Drop those
Python
parentheses.
3.14 is gonna be cool.
Amazing.
Right. And also, we mentioned this in the past, but now all always supported hash functions and hash-based message authentication codes, so-called HMACs, are implemented using verified implementations from HACL star, that's the High Assurance Cryptographic Library, instead of having our old homegrown implementations. So that's also thanks to Benedict Tran, and there should not be any functional difference save for potentially just being more secure because those implementations in HACL star are verified. So the last change to put there was actually the HMAC part that took a lot of effort to actually land. So congratulations, this is very cool to have.
Amazing. And the last thing that we have is fnmatch.filterfalse for pattern exclusion, and that was added by Benedict Tran in PR 121185, which is the only
Yeah, so that's pretty cool because that's the inverse of just filter. But every now and again, I'll be like, yeah, I would use that if that were there. So finally, Benedict made it work. I'm happy to see it.
Amazing.
So Bugfixes.
All right, Bugfixes. We have David Murray, the key maintainer of the email package. Wow, I thought it was Barry Warsaw. Okay, well.
They're
friends, no?
Barry Warsaw probably started the package. I don't actually know the oldest history of that, but R. David Murray used to be the sort of key maintainer for like a long time, and then he sort of had other things happening in his life. He disappeared, but now he's more active again.
All right. Okay. So he is more active now, and thanks to Srinivas Reddy, now header names passed to the email message objects are validated according to RFC 5322.
Like it happened in the past that, any string would be accepted and it would only fail later on when you actually try to serialize the message, which wasn't really a good experience since at that point you didn't know what was the moment in which you corrupted your email message. So now it's going to be much easier to figure out that, okay, this is the moment we're introducing something that is not valid by RFC. So that's great to see.
Right. It's always good to know when you corrupted something.
Yeah. And I didn't know this, but some people apparently are making exception objects that are falsy. I don't know why you would do this.
This reminds me of my favorite enum that I have ever seen at my current company, which was there's an enum called truth value, and it has 3 values. One of them is true, false, and the third one was
maybe
file not found.
Wow.
Amazing.
Yeah, because like maybe was this year's April Fool's PR.
No.
We actually,
right.
Yeah, like, we're joking around, and then some crazy person actually implemented maybe keyword in Python.
Wait, it was Nikita, no? Sobolev?
Oh yeah, so Nikita did, but then you also like extended this so that you could...
No, but I just violated the parser as much as possible because like I wanted to check if you could do maybe if maybe else maybe no maybe is maybe else maybe.
Yes,
like I wanted to support that and also support match maybe, case maybe. yes, that I wanted to say, and the parser works with that, like it handles that. Amazing. Yeah,
pretty cool. But in any case, I'm mentioning just exceptions that for whatever reason are a bool of exception is false. Those were sort of curveballs for process pool executors. Turns out that inside the process pool executor code base, you just had a bunch of if exception tests. And those were just falsy for an existing exception that is falsy. And then you would just swallow them. So the process pool executor wouldn't show them to you, which was obviously not good. So now Yves Duprat fixed that. And yeah, process pool executors will not ignore falsy exceptions anymore.
It's kind of weird, but yeah. Tiangao fixed line cache guidelines for frozen modules, which makes debugging frozen modules with PDB nicer, which is great because we are keeping having more of those. So, having sort of that is very cool.
Yeah, exactly. And Nikita Sobolev fixed a crash in, turns out, context vars. Now that we use them more, we're going to test them more. So when using context var with an unhashable key, you could get a crash. So now Nikita fixed this. And finally, we have a bunch of curiosities that I wanted to let you know about because there are changes that are just, either interesting mostly for us core developers, but also maybe interesting for you that are not really exactly 100% like CPython or its repository. So, first of all, news from PyPI, the paid organizations feature that people asked me about in the past a lot, picked up steam now, with close to 2,000 organizations approved by the PSF. There's another 6,000 in review, but it's going pretty fast now. He's going through them very quickly. So in an organization account on PyPI, users from an organization or community project can assemble into teams and collaborate on projects. And you can see this already where, for example, now on PyPI, you can see that the ZOP organization is an umbrella for 391 PyPI packages, and that includes ZOP interface, the Grok web framework, ZODB, and many, many others. But each of those, if you go to their PyPI project, presents this sort of field that says owned by ZOP Foundation on its PyPI project page. And this is not only cool to see, but it allows for something that was annoying in the past, where if a maintainer stops being active and this project is used by many, many other people, now it automatically becomes a support request. Somebody wants to keep maintaining the project, but they cannot upload anything more. So forming organizations for stuff like that, putting your small projects in an umbrella of a larger organization, all of this will help us actually having open source being more sustainable, for the long term. So that's great. But also for companies, a lot of them like Bloomberg and ARM and so on were already accepted. They already have organizations on PyPI, can now sort of put their own projects under the organization umbrella on PyPI.
Fantastic. Another important change is the CLI bot. You have some story here. What is the story, Gukish, of the CLI bot battle?
Yeah, so the one that we used before was written externally, and it was a Next.js application, which made it annoying for us Python developers to actually hack on it and add features that we wanted. So now the PSF staff with E. Durbin again spearheading this just threw that away and replaced it with a Django-based implementation that is now maintained by us internally. And this is also served using Cabotage on PSF infrastructure. So that significantly lowered the cost while there's already new features on there. And more are coming. So this is nice to see because essentially now like we have a solution that is more tailor-made for like CPython.
Right, fantastic. That's and it has a nice new comment I have seen, right? Because like now it's added at the end on a bunch of things.
Yes, it is formatted nicer, and it's like you can actually ask it for whether you signed the CLA for which emails of your GitHub account and so on and so on. So it is already becoming better, and it's going to get better in the future as well. And the PSF staff is fully now kind of in PyCon US preparation mode. So we're going to let them do that. But after PyCon US, there is a bunch of small features that people asked for in the CLA bot for years, and those are going to be coming soon.
Right, fantastic. Another cool new curiosity, new section. Is that regression tests are now treat warnings as error. Not in all the test suite, by the way.
Not in Socket, I guess, right?
Yes. Because another place. Test spec parser. Yes. Those because those call setup tools and shit. But anyway, so thanks to Thomas Greiner. This was not an easy change to do.
Sure.
Yes, but it's very cool because now we can catch a lot of the problems that we ourselves create for us.
What we had a lot was just, ignoring warnings, and just ones that did appear, you just couldn't see them because most of the time you don't run with verbose and whatnot. But like now, like the situation is much cleaner. So thanks for that work.
All right. Ken Jin made it so LTO training, LTO is linked time optimization, which is what basically grabs all your object files and creates a better version. This can run in parallel when you use -J, the make parallel option. Basically, it achieves this by passing LTO partition known to the flags of GCC, which is fucking fantastic because this was the slowest step when you build LTO.
Yes. I complain about that a lot. Yes.
It could take minutes. Disgusting. I think the worst one is arc, like when it increase the archive. That's the other one that is annoying. Anyway, fantastic. Thank you, Ken Jin. Fantastic. And this can not only like significantly shorten build times, but it makes us very happy. So we love you, Ken. Fantastic
Yeah,
work.
this is great both for developments locally and also on CI and build bots that we pay for, because even if you have multiple cores, if they just sit there waiting, you're not paying less. You're paying the same like for minutes spent. So now like that we're actually using all the cores that we have in a particular build bot or on GitHub Actions, like that's gonna be better. But I wanted to just like
What?
yeah, like I want to mention that this was a very controversial change.
How so?
It sounds like it shouldn't, right? Because it's like, okay, let's just
Because
make things faster.
the lobby of CPU usage
No,
is against it.
it turns out that to introduce it, we had to. Well, by we I mean Ken. Ken made a tiny change that's not in the final version of the PR, but like in the middle of it, it was like a tiny change to the make file that was like, okay, like we need to make a change, and it just added a bunch of pluses in front of the commands executed. And I was like, I've seen this in the past, but I since forgot what that was doing. So I looked into it, and it's like, oh man, like we need to get rid of makefiles. Like, come on, this is another case of like XZ vulnerabilities where you can add plus and the meaning of everything changes. It's just, like the syntax of it was very, very kind of small, but makes like kind of for big consequences. So Thomas complained about this, and like Ken ended up reverting most of the pluses added. But yeah, like this, if you look into the review of that PR, there was unexpected controversy because of that.
Oh, so let me see if I remember my make foo the plus. This is not the echoing, right? No, because
No.
No, this is the forcing. It forces the execution of the command,
Yes.
no, something like that.
Yes, exactly.
It's because the recursive make thing, right?
Yeah.
Like, the make on make.
Yeah. So all of it goes to show that even things that don't look conceptually controversial might be controversial due to their implementation. Or you might just get bogged down with details about how to actually make this work so that nobody's upset.
Oh man, but that is diceyable. Like you cannot use the plus. Like man, you do minus Q and then it just complains about shit. Like
yes.
No.
So now there is no
Dangerous.
but the initial version did have that. So it's
right.
It's very interesting how kind of. I actually didn't quite follow why that was required when the final version doesn't do it, and it's fine. But like I followed the controversy about like actually having plus, and this just gave me so much sort of like I don't know, flashbacks of the XZ situation, because that was exactly like a dot there.
Is the recursive make shit? Is the recursive make?
Yeah.
It's just to force the recursive make to run.
All right, and
it's disgusting.
And let's finish with a detail that I also kind of stumbled upon, where saying if false or if type checking is popular to specify types for type annotation purposes that you don't want to be executed or appear at runtime. In fact, we do plenty of that in PyREPL as well. So due to a bug in the implementation of PEP 649, types in those blocks were still evaluated by Python.
Jesus.
Which is weird. Yeah, but now Jelle Zistra fixed that, and this is no longer the case.
Evaluated? No. Evaluated? You mean compile? Evaluated?
Well, yeah, like one leads to another, right? Yeah.
I mean, sure, but like, how can it be evaluated? Evaluated as like if I put print, it prints? No. How can that be? That's disgusting. No. How can it be evaluated?
That's what the issue was called. Conditional blocks in class definitions seem to be evaluating types even when those conditions are false.
Evaluating types. Okay. That's different. Evaluating types, right? That's slightly...
Oh yeah, the type annotations there, yes.
That's slightly different. I think it's just that it compiles it. Like, so it doesn't really run them. It cannot run them. I think it just compiles them, right?
Let me explain. So those annotations that end up in a class because of if type checking, right? Like that might also be the module, right? Because the module also has dunder annotations. Things that are in if false, they shouldn't even land in dunder annotations. You see what I mean? Because later on, when you actually address dunder annotations, then you're gonna evaluate it. But you are now evaluate something that was under if false, so it should never actually land it in dunder annotations.
Absolutely, it's more than like. Man, this reminds me of that horrendous issue I had to fix like 6 million years ago with the like conditional evaluation of like the if false in the compiler, like just to raise if you do continuous save functions, but you surround that by an if false, because before the compiler was not complaining about that. And I added this like disgusting thing like in the compiler basically checking if you are in one of these, but like it was a and do not emit bytecode or something like you turn off the compiler, but the compiler still is grumpy. But like it doesn't run them. Like it's still, if you print, it won't print. It's just that it compiles.
No. Like it is purely that like if you have a statically false, kind of conditional, that thing should not actually end up in dunder annotations of that module or class.
I'm also checking the change, and they literally did the same idea. Now the compiler has this new thing called unconditional block.
Yeah.
But mine will be recursive, which like here is used as a boolean, but like the correct thing to do is to use as an integer. Because like you want to know if you are recursing into.
All right, okay.
Because you can have if false, if true, if false, and you want all to be false just because you are inside the first one, right?
Right, like for type annotations, that's rare, but like, okay, like technically you're correct that it would be more...
Of course, the best kind of correct.
Yeah, in any case, we are reaching 2 hours now again.
No.
Every time.
Quick, we need to finish before 2 minutes, so we can say that we need less than 2 hours.
No, we are less than 2 hours because of your like bad internet connectivity in Great Britain,
okay,
so we're fine.
Okay.
But still, we're close to 2 hours.
Well, people,
every single time.
Don't garbage collect us for this. we are in a cycle of friendship.
No,
but
you know why the episodes are so old, because we are the old generation.
No, man. You know that now Fortnite apparently is Fortnite is old for old people. I don't play Fortnite particularly because I still think it's for young people. But apparently the kids these days think that Fortnite is for old people. You know what the kids these days play?
You know what my 17-year-old plays?
Yeah, Minecraft. I don't need to ask. It's fucking Minecraft.
Team Fortress 2.
Time is a flat circle.
Time is a flat circle.
Time is a flat circle, dude. Wow.
Yeah.
Okay, but that it means that no, because your teenager is kind of like ending the teenager years, right? Like so he's a young adult, but the new kids are playing Minecraft again. So like again, like this confirms that time is a flat circle, because like now it's going through the whole movement yet again. But maybe we wait enough. We are young again, no? Like kind of.
I don't want to get into like religious discussion here, like on this side of the stop record button.
This is so depressing.
But
so
yeah, like
people don't be old. Be young.
Getting old sucks, but the alternative is worse.
Yes. But you get more peps. Well, people, enjoy your young years. Don't get collected.
Yeah, and see you in 2+ weeks.
Yes, maybe Lucas has finished the syntax fucking highlighting. Fucking Apple. Fucking Apple. Goodbye.